Now it's time to start solving equilibrium equations over a particle. So let's have a look at this tug of war game where four teams are pulling at a rope and assume that at some point in time it's in equilibrium. When we create a model of something in statics, we try to isolate the thing that we are looking at from the rest of the world. So let's say that in this case we are looking at this center point of the game, and we want to look whether this center point is in equilibrium. To do that, we can isolate this from the outside world. So make a virtual cut in all ropes and remove all the teams from our model and replace these teams with the force that they are pulling with. So if we would create a so-called free body diagram of this center point, we will have the center point, and we will replace all teams by the forces which they act on this center point. So we have a force caused by the red team, a force from the yellow team, a force from the blue team, and a force from the green team. With such a free body diagram, we also need to define the direction in which we will write equations. So we need a coordinate system. Well, here it's very logical to define a coordinate system in horizontal vertical direction. By default, we assume that this is the coordinate system that we will use. And especially if you use a different coordinate system, you should very explicitly draw it and mention it. Well, and with this free body diagram, we could start writing equilibrium equations. So now let's have a look at another theoretical problem. So let's say it's a similar problem. So there's some particle in the middle, but now we have three teams. And so we have one particle and we have three forces. And we define a coordinate system in x and y direction. To calculate equilibrium of this system, we need to write equations in the directions of our coordinate system, which are in the horizontal x direction and here the vertical y direction. To do so, we need to know the contribution of each force in these two directions like we discussed before. So the question is, how do we decompose these forces? And now let's assume that we have a force F1 at an angle of 45 degrees. How do we know the contribution of F1 in x direction and the contribution of F1 to the y direction? So we want to know F1, and then we write comma x, and we want to know F1 comma y. F2 and F3 are already oriented in the directions of the coordinate system, so we don't need to decompose them. But how do we decompose this force? Well, if we look at this F1 force, the decomposition is the we call it the projection of this angle to the both axes. So the F1x component will be this contribution, and the F1 in y direction will have this specific length. So if you look very carefully to these triangles, we can also draw it like this. So here we have F1, and this length will be F1x, and this length will be F1y. So here we already have a triangle with a 90 degrees angle. So we can use our sine and cosine rules to define the values of this F1y and F1x. So if we say this is our angle alpha where we look at, then we know the rules that the sine of alpha is the opposite divided by the hypotenuse, and the cosine of alpha is the adjacent divided by the hypotenuse. So in this case, we can say that it is the sine of alpha is equal to f1y divided by f1, and the cosine of alpha is f1x divided by f1. In this case, alpha is 45 degrees, so we know that both the sine as well as the cosine of alpha are half square root 2. So we can solve it and say that f1 in y direction is half square root 2 f1, and also f1 in x direction is half square root 2 f1. So from these angles, there are some basic angles which you are assumed just to know. So if we have the angles of 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees, you're assumed to know the values of sine alpha and cosine alpha. If you don't know, you should rehearse them. So the cosine of 0 degrees is 1, the sine of 0 degrees is 0, the sine of 90 degrees is 1, the cosine of 90 degrees is 0. Both sine and cosine of 45 degrees are half square root 2, which we just used, square root 2. And then the sine of 30 degrees will be half, and the cosine of 30 degrees will be half square root 3. And for 60 degrees, it's exactly the opposite, the other way around. So half square root 3 for the sine of 60 and half for the cosine of 60. These are values that in our exercises we use them quite often, so you're just assumed to know them. Well, then these are standard rules which you're assumed to know, but then I just want to discuss one other way in which we can also decompose these forces. So let's have a look at this problem where I have a cable and a pulley and a mass, and here I have a length 3 and a length 4. And what I want to discuss is that sometimes you can also use the geometry of the system as a ratio to decompose your forces as well. So in this case, the cable is, so if we draw the cable, this part of the cable, we know that, let's say this length is 3, this length is 4, and by using the square root of a squared plus b squared, so square root of 4 squared plus 3 squared, it follows that this length will be 5. In a cable, the force always acts in the direction of the cable. So we know that the direction of the force in this cable will always be in the direction of the cable. So when drawing a free body diagram over this in the surrounding of this pulley, we will have a free body diagram which looks like this. So there will be a cable force, and then downwards there will be a force which is mass times the gravitational constant. So how to decompose these forces, so how to calculate Fc in x direction and Fc in y direction with our standard coordinate system if we know this geometry. So what we know is that the ratio between the geometry and the forces will be the same. So the ratio of 3, let's say, over 4 or over 5 will be the same as the ratio of the forces. So if we draw the same triangle with the forces, we have our cable force, we have the component in x direction and the component in y direction. So we know that we can write that 3 over 5 is equal to our component in y direction over our cable force, and 4 over 5 is equal to the component in x direction over the cable force. So using this, we can thus write the component in x direction is 4 over 5 Fc, which shows you that sometimes instead of, another approach would be to first calculate this angle alpha and then plug this angle alpha into your equations, which is possible as well, but it's much easier sometimes to use this geometry. So now that we know how to decompose these forces, the last thing that we have to do is calculate our equilibrium. So again, we have this problem. So we had F1, F2, and F3 in an angle of 45 degrees. And to calculate equilibrium over a particle, we need to look at the sum of forces in x direction and sum of forces in y direction. So what we have to do is just write out these equations. So we say that the sum of forces in x direction, being to the right hand, being positive, is equal to the x component of F1, F1x. F1 acts in positive x direction, so this is a positive value. And the F3 force acts in negative x direction, so we can say minus F3 is equal to 0. And writing this, so writing is equal to 0, is a very important thing. So in statics, we say that the sum of forces is equal to 0. So when writing statics equations, you should always include this is equal to 0. And sometimes people forget it, but there is only an equation if you state that it is equal to something, and in this case it's 0, so you should always include that. Well, and then from our previous discussion about the decomposition, we know that F1 in x direction is equal to half square root 2 F1 minus F3 makes 0. Well, the same equation we can write for the sum of forces in y direction, and then upward will be positive, is equal to the contribution of force 1 in y direction minus F2, which acts in negative y direction, is equal to 0. And again, F1 in y direction was equal to half square root 2. F1 minus F2 is 0. So these are our two equilibrium equations. And what we do normally is that there are, when two equations are, when we can write two equations, we can solve two unknowns in the equation. So here are three forces, so we cannot solve three forces with two equations alone. But let's say that if we would say that force 1 is known, so for example, force 1 is equal to 1000 Newton, then we could use, we could solve for F3 and F2. So F3 will be half square root 2 F1, which will be something like in the range of 700 Newton. And the same for F2, we would be able to solve this.